Welcome to your premier destination for mastering concepts. Crack IIT, NEET, and all board exams with us.
To understand how machines retain magnetic memory, we have to isolate the fundamental physical interaction. We start with a completely unmagnetized piece of ferromagnetic material placed directly inside a solenoid. When we run a current through the wire coil, we generate an external driving force. In physics, we call this the magnetizing intensity, or H. It is measured in amperes per meter, and it acts as the outward pressure trying to force the material into a specific state. In response to that external pressure, the material reacts. We call this internal physical response the intensity of magnetization, or I. It represents the material's magnetic dipole moment per unit volume. The external field pushes, and the internal dipoles align. The intuitive assumption here is that these two variables should scale perfectly together. As you increase the external field, the internal magnetization should predictably and linearly increase right alongside it. But an anomaly occurs when you cut the power. When the external field drops entirely back to zero, the internal magnetization does not immediately disappear. Inside the material, the magnetic domains stubbornly refuse to randomize. They lock into place, holding a structural memory of the applied field. This specific phenomenon is called hysteresis, a Greek word meaning to lag behind. The intensity of magnetization lags behind the external magnetizing field. Because of this lag, the relationship between the external field and the internal state is nonlinear. Mapping a complete magnetic cycle onto a graph reveals a geometric fingerprint that dictates exactly how that material will perform in an engineering context. This chart displays the complete IH hysteresis loop for a ferromagnetic material. To see how these values are derived, we'll trace exactly how this curve is plotted, starting from an unmagnetized state. We start at the origin. The horizontal axis tracks the external field, H, while the vertical tracks internal magnetization, I. Increasing the external field sweeps the internal magnetization upward, tracing to point A. This is physical saturation. Here, all magnetic domains are perfectly aligned. Pushing more external current into the solenoid beyond this point is useless. The material has reached its absolute physical capacity to carry magnetism. Since we can't push the magnetization any higher, the next step in the cycle is to dial the external field back down to zero. Instead of retreating down the original path, the line diverges. The internal domains stay largely locked in position, following a new path down to point B on the vertical axis. This vertical line segment, from the origin up to point B, is known as retentivity. Physically, this segment represents the residual, permanent magnetization that survives inside the material even when there is zero external power holding it there. A material that charts a massive retentivity segment on the y-axis is structurally suited to function as a powerful permanent magnet. But if the material holds onto that magnetism at point B, it presents a mechanical problem. How do we force the internal magnetization completely back down to zero? The only solution is to apply a reverse external field. We have to push negative H to actively fight the residual magnetism inside the structure. Applying reverse current forces the internal alignment to collapse, tracing down to point C on the negative horizontal axis. Internal magnetization becomes zero. This horizontal segment is coercivity, the exact reverse external field required to wipe the material's magnetic memory completely clean. Coercivity measures exactly how fiercely a material resists having its internal state changed by outside forces. It acts as a defensive shield against demagnetization. Continuing the reverse field hits negative saturation at D. Dropping the field reaches negative retentivity at E. A forward field overcomes positive coercivity at F, closing the cycle at A. The true engineering cost is the total geometric area enclosed within the loop. Cycling magnetic domains back and forth forces them to constantly grind against their own structural walls. That internal friction creates tremendous resistance. That intense internal friction converts magnetic energy directly into physical heat, radiating outward and stripping efficiency from the entire system. In applied physics, the geometric area of the IH loop is exactly equal to the hysteresis energy lost as thermal heat per unit volume for every single cycle. This table compares the distinct retentivity and coercivity properties of soft iron and steel. Because their atomic structures differ, their hysteresis loops yield radically different geometries. Soft iron plots a narrow, razor-thin loop. Its low coercivity makes it easy to flip, and its tiny area guarantees low heat loss. Conversely, steel produces a broad, inflated loop. Its massive coercivity resists demagnetization, but that large area causes massive heat loss when cycled. Engineers map these exact dimensions to align the material's geometry with the thermal and magnetic constraints of a machine. Because soft iron sheds little heat, it operates safely in environments that rapidly alternate magnetic fields. It is the core material holding together industrial electromagnets and power transformers without melting down. Alternatively, steel's high coercivity protects its internal alignment from accidental interference, making it the required material for permanent magnets found inside loudspeakers and precision motors. The hysteresis loop establishes the boundary between a material's atomic response and its industrial utility. These measurements allow us to map invisible internal states directly onto the practical requirements of modern engineering. Thank you for exploring the universe with us. Subscribe to Fundamental Physics for more.